The next discussion for this chapter is towards the end of the chapter. We don't always have time to cover everything in a semester, and so this semester we probably won't really get into any details about metallic and other solids. So we're going to think instead about discussing phase diagrams and relative densities of liquids and solid phases of a substance from a phase diagram, as well as what a stable phase or phases of a substance might be for a given temperature and pressure using a phase diagram. All right, so there's our word of the moment that we need to relate to. All right, what a funky looking plot. We have a peculiar set of axes because pressure is on the vertical axis and it is not necessarily linearly plotted, so that makes it really curious. And the same thing is true on the bottom axis. It's temperature. So pressure and temperature are shown here, and Celsius temperature, atmosphere's pressure. And we're looking at solid, liquid, and gas at different things here. And these different colors and different lines, what do we see here? Well, first of all, the normal melting point is shown in here in the middle. And it appears to be at 1 atmosphere and 0 Celsius. Oh, there's a clue. And the normal boiling point is also shown here, where we have 1 atmosphere and 100 Celsius. Well, that tells us right off the bat, I hope, what the substance is that would have these properties. It would be good old H2O. So this is what we call a phase diagram. The different regions are colored just to make them contrast and make them obvious to you. In addition to the normal boiling point and the normal melting point, those are the melting and boiling points at 1 atmosphere. That is the definition of normal, is that they're going to occur at 1 atmosphere. In addition, we have something else that we haven't yet discussed, we will mention now, is called a triple point and a critical point. And we need to understand what a supercritical fluid might be and the significance of this boundary line between the solid and the liquid that it's, in this case, has a negative slope. Well, here goes. A normal boiling point is the temperature at which boiling occurs when there's 1 atmosphere of external pressure. That's a definition that was shown already when we were looking at vapor pressure curves. And the normal melting point is corollary there, so it's a temperature at which melting occurs at 1 atmosphere of pressure. The triple point is an odd thing. It's a point at which all 3 phases coexist in equilibrium. Let's go back and look at the graph. So the triple point in this graph is way down here at the bottom, and it has the gas and the liquid and solid all intersecting here. So this is why we call it a phase diagram, because all the phases are represented and what temperatures they will occur. So what can we do with these kinds of graphs? We can also talk about the critical point, which is at the top. It's the combination of temperature and pressure beyond which the gas cannot be liquefied. So the critical point has 2 features or 2 aspects. The critical temperature, beyond which you cannot liquefy a gas, regardless of the pressure. In other words, it's too hot. And the critical pressure, beyond which you cannot vaporize a liquid. So you can either make it in a gas or a liquid. You cannot make a gas beyond that pressure, and yeah, you can't vaporize it into a gas regardless of the temperature. So it's kind of an odd place. And beyond those points of the temperature and pressure, when you're beyond that, you have reached supercritical status. So it means we're beyond the critical point. That's what the super means. So the state of matter beyond which you have neither liquid or gas, and it's kind of an odd entity, but you can find it off of these phase diagrams. Now, it's only so much we can do with them, but you can kind of see what odd conditions of temperature and pressure might be required. So let's go back to the water diagram and double check to see what it looks like for the critical point. The critical point for water is way up there. And apparently it's at, what is this temperature here? 374 Celsius. Funky number, not that you have any reason to know what it would be. It's a Celsius number. And the pressure is, oh my goodness, a lot of pressure, 218 atmospheres. That's crazy high pressure. So you'd have to get water very hot and very high pressure to reach that critical point and the point of being a supercritical fluid. Not easily done. So here's a diagram or a photograph representing what it looks like when you're at a triple point, the point at which all three phases exist in equilibrium. They coexist. So in this bubbling flask that's closed from the air, there's boiling liquid, and yet there's solid present in there. So you got to have really weird conditions to get that, but it's what a triple point looks like. You can kind of see the solid present in the boiling liquid. And so if it's boiling, there have to be liquid and gas, but there's also solid too. So it's weird conditions of pressure and temperature that allow that to occur. So what else can we do with these phase diagrams? Here's another one for carbon dioxide, which is a little bit different from the one for water. Each substance will have its unique phase diagram representing the points at which the liquids turn to solid at normal pressures and temperatures, liquid turns to gas, and at all kinds of other temperatures and pressures. So in this case, we need to be able to look at this and see what's going on. So first question up there is what phase is present when the temperature is minus 60 Celsius. And notice they're not necessarily drawn to scale, so you kind of have to guesstimate a little bit where they belong. And a pressure of 0.75 atmospheres. Well, how about would that X there about be the kind of the right idea? So it's less than 1 atmosphere and a little colder than minus 56, whatever it's worth. So what phase is present? Well, apparently from this view, it would be a gas. Now, the next one is, how do we read this, in other words? So minus 35 for temperature and pressure of 18.6. Stare that one down a little bit. Where do you suppose minus 35 would be? Well, it's a little warmer than minus 56, but 18 atmospheres, 18.6, well, somewhere up there, making a guess, somewhere in that vicinity. So at those conditions, this is carbon dioxide, good old CO2, is apparently going to be a liquid. So you got to have weird conditions. Rather cold but high pressure allows CO2 to become a liquid, not something we encounter very often. The third one here is minus 80 Celsius. So that's way down there at the left, and the pressure of 5-something atmospheres. Well, it's above that other line there. And so it's up there in that region. So apparently in that set of conditions, carbon dioxide is going to be a solid. So you have a way to interpret and predict the solid, liquid, or gas state of a substance using a phase diagram. Now, the key little oddity or curiosity about a phase diagram is noticing the direction of the positive or negative slope of a solid liquid boundary, because here for carbon dioxide it is a positive slope. If you remember how to do y equals mx plus b kind of thing, the m value is going to be positive for carbon dioxide, and how we interpret that will become more obvious as we look at some more diagrams. So this one for CO2 has a positive slope, notice. Let's keep going. So the thing that we want to remember is that the boundaries are going to slope towards the less dense medium. So which is going to be less dense? In this case, the liquid. For carbon dioxide, it slopes towards the liquid, and that's the nature of carbon dioxide as a liquid. Not that you run into it very often because it's normally going to be a gas most places. At 1 atmosphere, you are going to get a transition from solid to gas as it warms up, and that's called sublimation. So you don't even see liquid unless the pressure gets really high. But this diagram shows us that, in fact, CO2 is less dense as a liquid than it is as a solid, which makes some sense. And that phase diagram represents this. So let's use this diagram and ask some more questions. If we're looking at the phase diagram for carbon dioxide again, at what temperature does the triple point occur? So if you remember what the triple point is, solid, liquid, and gas in equilibrium, it's where all those lines intersect on this graph. Ta-da, there it is. And that'd be, what temperature are we looking for? Apparently it's that minus 56.4 Celsius. It's just a characteristic of carbon dioxide. All right, what else can we ask for this kind of graph? Using the following phase diagram, same one for CO2, what's the boiling point of carbon dioxide at standard pressure? Well, boiling means what? Boiling point means liquid to gas, typically, right? The point where that occurs. So liquid to gas at standard pressure. Standard pressure, well, it's not even going to be a liquid, is it? So it's actually going to be skipping the liquid and going from solid to gas, because standard pressure is 1 atmosphere, if you recall STP from our gas law conversations. And so at 1 atmosphere, apparently it turns to a gas without so much as finding the liquid at that point down here on the graph, and that is the boiling point of carbon dioxide. It is also the sublimation point in this case. So sublimation is the same thing. There isn't a boiling process per se for CO2 at standard pressure. All right, let's do one more one more diagram about the phase diagrams, or two. So here's water by comparison to carbon dioxide. And so this is where the boundary between the liquid and the solid is going to be different. It has a negative slope between liquid and solid for water because solid water, ice in other words, is less dense than liquid water. Because of the nature of ice, it has a lot of spaces between the water molecules in an ice crystal, which is indeed why it is less dense, and ice can therefore float on liquid water. You've seen floating ice, like icebergs, like ice in your glass. Haha. So the solid-liquid boundary line has a significance that tells us when something is more or less dense. In the case here reflects the fact that ice is less dense than liquid water. Okay, so let's look at the phase diagram and ask some questions. Then how about what happens to water when the temperature goes from 48 Celsius to -4 at a constant pressure of 6.5 atmospheres? Wow, so speculate, estimate, guesstimate, where do you suppose that would be? So 48, notice the temperature graph goes from 0 to 100, so how about there, and somewhere above 1 atmosphere, it's up there somewhere. And now we're going to change the temperature and go towards -4, so it's going that direction. What's going to happen? Well, can you tell if it's going to get to -4.4? Can't say for sure from this diagram, but you might. You might assume that that's going to be just a little bit beyond here, and so probably the liquid turns into a solid at that temperature. If not, it's very, very close. Okay, second possible question here. When the pressure goes from 85 to 226 atmospheres, so you've got to start at 85 atmospheres. Oh, that's a ways up there. And it's going to go to 226 atmospheres. Well, let's see, where would that be? At a temperature of 380. Oh, it's way over there on the right, somewhere over there. And it's going to be increasing the pressure from 85, we have no idea where that is, towards 226, which is apparently above the 217 something we see for the critical temperature. And so this would suggest that the gas is going to go to a supercritical fluid. Interesting. It's beyond the critical point. So the gas turns into a supercritical fluid if you're at that temperature and those pressures there. Okay, so these are the ways we use phase diagrams in trying to explain how the changes of phases occur in given substances. Water and CO2 are the most common ones. You could find them for other substances, but these are informative when you understand the significance of the solid-liquid boundary line in understanding the densities of the liquid and the solid. The line will lean towards it will slope towards the less dense phase. All right, good luck with your studying. I hope you find this useful. Ask lots of questions and see you in class.